here we are with Gauss's law. All right. Do you guys remember let me write Gauss's law. And we'll sort of go over what it says. So we've been dealing primarily with this part. So we started by sort of defining flux, okay? And flux is roughly any vector field as a dot product of the area that the vector field passes through, okay? And the other way to talk about this is divergence. Remember this thing, okay? And you can see the divergence is not zero. And what does it mean when your divergence is not zero? I think physically what it means is there's some sort of source for your vector field inside the surface you've created, right? So in the case of electric fields, what would the source be?
Like electrons?
Yeah, like charges, right? So either positive or negative charges. So this flux is not zero. And the flux is this, okay? And this is the complicated part. So this is measuring the divergence of the electric field. So that's how much the electric field goes out or comes in. Because remember, if it just passes through your surface, what's your flux? No flux,
or neutral.
right? Yeah, it's zero.
Yeah,
zero
zero.
flux, which means there's no charges in the surface, okay? So we've been sort of skirting around this, but this is the actual formula. And so this is the whole thing. And what are we going to use it to find? So what did we spend the whole first chapter trying to find? Electric fields, okay? And what did we have to do to find electric fields last chapter?
Coulomb. Integrals.
Yeah, we had to integrate Coulomb's law. Did you guys like that a lot?
No.
Yes.
Okay. Some of you did. Okay. Well, so what do you think we're going to find with Gauss's law?
More integral, double integral.
No integrals.
Which thing are we going to find? Electric field, okay? We're still finding electric fields. Okay, so we've spent a lot of time calculating flux, and the whole point of doing all those flux problems was to sort of get you in line with the concept of what Gauss's law is. But how we're going to actually use Gauss's law in most of the problems we do and on the test is to calculate the electric field. Okay? So realistically, we only use this part of Gauss's law for most problems. Okay? So we have to figure out, we have to create a surface, and we've already got a lot of practice creating these surfaces. All right? And then we have to figure out how much charge is enclosed in that surface. Okay? And we're going to go through sort of the technical details of this, but that's the basic idea. We want to calculate electric field using just this part of the equation. We introduced flux as a way to understand why, because this is the part that's hardest to understand, right? This weird divergence math. So we sort of introduced flux to show you why this is a thing, like where this comes from. All right? And you notice the last three problems we solved for flux, what was the answer?
Q over epsilon naught.
Yeah, we kept getting Q enclosed over epsilon naught. So even if it's an infinite thing, the charge enclosed is not infinite, right? It's just the amount of charge inside your Gaussian surface that you create. Okay? So this is Gauss's law. And using Gauss's law, you can calculate the electric field much more easily than when you integrate Coulomb's law. Okay? It looks like a much scarier integral, but the key is to set the problem up in such a way that you never actually do an integral. Okay? You end up with the integral of dA, and then you just have to know the surface area of something. Okay? And you can pretty much guess what kind of shapes we're going to use. Right? We have spheres, we have boxes of any sort, right? And then we have cylinders. And that's pretty much it for what we're going to use for Gauss's law. And that sounds simple, but there's lots of different ways these things can manifest themselves. Okay? So here's the electric flux through any Gaussian surface. This is the charge inside the Gaussian surface. Sometimes it's called Q in, sometimes it's called Q enclosed. And this is the electric field at the Gaussian surface. Now that's a really key point, right? It's not the electric field everywhere. It's just the electric field on the surface of the Gaussian shape that you create. Okay? So, if you can create a useful Gaussian surface and you know the charge inside it, it's really easy to calculate the electric field. And you're going to have some very nice symmetry. And this has to do, the main thing is to also understand, like, we don't use the electric flux very much in the actual calculation, but it's still an important concept. You still need to know what it is, okay? So let's talk flux. Looking at this equation, this is very distracting. What does this say?
Epsilon naught.
Charge over epsilon naught. So the flux, this talks about the shape, but this doesn't, right? This says flux has to do with just the charge. And we spent a lot of time proving that last time by doing a lot of long problems, okay? But what this says is flux deals with just the charge. So the flux here is going to be the same as the flux here. It's going to be the same as the flux here, okay? And these two are different because they have different charge. So the shape ends up mattering a lot less than you would think. Now, this is why picking a good Gaussian shape is good. It turns out this, and this all give the same answer. And you can kind of see why, right? Here, your area is bigger, but what happens to your field? It's smaller, right? Because you're farther away. Okay? So remember, this is a sphere, so the size of the sphere goes up by r squared, but the size of the field goes down by r squared. So those should exactly cancel. Okay? This is a little more complicated, and this would be an awful integral. Because what are the angles of the surface if you put a square around something that's spherical? All of these, okay? So you're going to get all kinds of angles. You'll know that a lot of the components are going to cancel, okay? But this is going to be a mess to integrate. But it turns out it doesn't actually matter. We know if this is Q and this is Q and this is Q, those give us all the same flux, okay? If you have one charge contained inside the surface, it's the same flux no matter what shape surface you make. And this is sort of the neat thing about this divergence theorem, right? Even though actually calculating it is tricky, the concept makes it simple. As long as you know the charge enclosed in your surface, you can know the flux, okay? And so the answer for this is going to be C, right? It only depends on the flux. If you have Q enclosed in your surface, you have one flux. If you have 2Q enclosed in your surface, you have the other one. Okay? And 2Q is obviously bigger than 1Q, so those are greater than all the Q fluxes. All right, let's try another one. This is, remember, flux is a form of flow. Okay, so is all the flux going in this surface coming out this surface?
Yes.
Yeah, it has to be, right? There's nowhere else for it to go. So if it comes in, it has to go out. It's flowing through it, all right? So that means the flux here through this surface should be equal to the flux here through this surface. And you're going to say, well, this surface is bigger, right? But what do we know, even if this is a constant electric field, what do we know about how we calculate flux if we want to actually do it with area?
Charge.
Is this perpendicular to this surface?
No.
No. So at this point, you're going to get less than you would at this point, okay? Because it's a dot product between the electric field and the surface area. So you can tell just by looking at this, you're going to have to do a lot of cosine theta, all right? Every time cosine theta is less than 1, that's smaller than if you just have perpendicular vectors, all right? So this is going to give you the same flux as this, even if you go through the whole calculation. But we know it is because we know what flux is. It's a flow. So anything that flows in here has to flow out here because these two surfaces form a closed surface. Okay? We have the same number of lines going in as we have coming out. All right? That's going to be equal flux. Yes.
Is that true for all cases, or?
Yeah, anytime you have a closed surface where you have lines going in and lines coming out in the same number, that means your net charge is 0. So yeah, you can tell, no charge in here,
Even
right?
if you were talking about a capacitor like you were earlier.
Well, this would be putting a surface like in between the plates of the capacitor. So you wouldn't have any, just anytime you have flux like in one side, flux out the other side that are equal, then you're going to have 0 charge in your surface. Okay? All right. So here's a little summary. This is mostly, we're not going to go in great detail on this right now, but it's for your reference as you're going through the notes, okay? This is how we use Gauss's law. This is the part we normally use to solve problems, all right? It's important to understand what flux is, but it's not always very important for the actual mechanics of the problem. So we first always draw a picture, and I highly recommend, if you're just starting out, using multiple colors, okay? Just because it's hard to keep track of all of the shapes. Then you choose a Gaussian surface. And remember, we went over the ways to choose a good Gaussian surface, okay? You want it to have the same symmetry as the charge distribution. So if your charge distribution has cylindrical symmetry, you should probably use a cylinder, okay? If your charge distribution has spherical symmetry, sphere. It's a good choice, all right? It's not too crazy. You want your electric field to always be tangent or perpendicular to the surface, so parallel or perpendicular to the surface vector, all right, which remember is perpendicular to the surface. And of course, if it's perpendicular to the surface or parallel to the surface vector, you need the electric field everywhere on the surface to be what? No.
Wait, what was the question? I was copying.
Oh, okay. So if you have parallel, if your dot product gives you 1, right? If your cosine theta gives you 1, what do you need the electric field to be at the surface?
Perpendicular.
So assuming you can't just make your the dot product 0.
Okay.
Electric field has to come out of the integral. What does something have to be to come out of the integral? Constant. Okay? Remember, if these vectors are parallel, you need electric field to be constant. Alright? And remember, this does not need to include all the charge. For the infinite line, obviously you can't make an infinite cylinder to enclose all the charge. You just enclose some of it. Okay? And even if you just calculate the electric field enclosing part of the charge, it'll still give you a general answer for something infinite. Alright? So on the left side, you have to find the area of the Gaussian surface. So if you get all this stuff right, you end up with just an integral of dA. Okay, an area integral of area. So you just need to know the surface area of the shape you picked. On the right side, you need to find the charge enclosed. And that actually ends up being kind of tricky, because the kind of electric field problems we can do with Gauss's law vary a little bit from the kind of electric field problems we can do with Coulomb's law. In Coulomb's law, we were always calculating the electric field outside of a shape, okay? Using Gauss's law, we can calculate the electric field inside of something. And I want you to imagine how hard it is to set up a Coulomb's law integral where you're inside of a sphere, okay? Even using spherical coordinates, you have to take into account all of the pieces outside of the point you're trying to calculate. And I hope they cancel, which they do, but setting up the math to do that is nearly impossible. So, if you're outside the structure, it's pretty easy, right? If you enclose a charge Q, what's the charge enclosed? Q, okay? If you enclose part of an infinite line or an infinite cylinder, it's just the charge density times the length you have enclosed, right? You enclose part of a sphere, it's just the volume of the sphere times the charge density of the sphere, right? But it's different. If you're outside the structure, you just look for the charge that's inside. If you're inside the structure, then you have to be careful with the charge density. Okay, you have to just figure out what percentage of the total charge is enclosed inside your Gaussian surface. All right? And then you just plug these things into Gauss's law. So once you calculate this and this, you solve for electric field. All right? So the important thing is just setting everything up. And drawing the picture is disproportionately important in this sort of work. All right?
Okay, so here we're going to try out a Gauss's law problem, and we're going to try it out on something we essentially already know the answer to, because we used Coulomb's law to calculate the electric field for outside of a solid charged sphere, and it looks pretty much just like a point charge, the only difference being that sometimes we replace little r with big R. But yeah, essentially big Q instead of little q, it's not that much different than a point charge. So we know it's going to have a nice spherical symmetry. We know the electric field lines are going to point out in all directions. And so let's set this up knowing what we're getting as the answer, because remember, now we're not solving for flux, we're trying to solve for the electric field. Just like we did with Coulomb's law, we're calculating electric field. So we'll start with this sphere of charge. So let me draw the sphere. Okay, and we'll make it a little bit prettier. And so that's a sphere of charge, and we'll color it in. Oops. So here's our sphere of charge. It has a charge Q, and it has a radius that we'll call R. Okay. We don't necessarily need to have this Q here. We'll just put it over here. All right. And we know that we want to use Gauss's law, and Gauss's law looks like this. So we're ignoring the flux part because we're no longer calculating flux. So it has to be a closed surface integral of E dot dA, which is equal to Q enclosed over epsilon naught. So this is our Gauss's law. Okay, so because we need Gauss's law, remember our electric field that we're looking for should look something like this, right? We have field lines coming out in all directions, like, oops, just like for a point charge, okay? And because this is spherical, you have to sort of imagine that they're pointing out towards you, and then there's some that are going into the page, and it goes out in all directions. So spherical symmetry, but it's hard to draw in 2 dimensions, okay? So that tells us that that's what our electric field's looking like, and that's what we're trying to calculate. We also have to decide what is our Gaussian surface going to look like. And since our Gaussian surface needs to be outside the sphere, that means we have to draw another sphere outside of our sphere. So we have this sphere that's outside the sphere. It should also be this lovely spherical thing, so just make sure we know it's spherical. So that means it's also this, and we can fill it in. So here we have this yellow represents our Gaussian surface, which is also a sphere. It's not a solid sphere, it's just a shell of a sphere, but we know that at each point, right, where this comes through, where the electric field makes contact with the sphere, we know we have electric field vectors that look like this. We know we have area vectors that are parallel to the electric field vectors, and they look like this, okay? Because of that, the area we're worried about here is the area for the Gaussian surface. So what's going on with the Gaussian surface? This Gaussian surface has a radius that's a little bit different. It has a radius that's little r. And we're going to call this little r. It's very important that we call it little r because it needs to be a variable, right? So it can be anywhere outside of the field. Capital R is a constant, meaning it has to be that exact size. But the Gaussian sphere is sort of a thing we make up in order to make the math easier. And so the R can be anything that's bigger than R. So in this case, we can write that little r just has to be greater than or equal to big R. And this is a constant. And this is a variable. But it has some limits. It has a range in which we can actually view it. Okay, so what we've done is we're doing the same Gauss's law process that we did when we were calculating flux. And then we also have to figure out from looking at the Q enclosed, what the charge is, and then this other thing is a constant, okay? So when we set this up, we can see that E can pull out because we see that all of these little E vectors, because we're all at the same distance from the sphere, E should be constant. E in general is not constant, right? We know that E is going to look something like KQ over R squared. This is for a sphere. We are calculating this, but we know what the answer is going to be because we've calculated this with Coulomb's law. So just so we know later, this is the answer we're planning to get. But in this case, just from the symmetry, just from looking at the electric field lines as we know them, we know we can pull E out. So we're going to pull E out, and then we end up with this surface area. And we also know that all the charge enclosed in this is just going to be Q, and still over epsilon naught. So our Q, that's the same. We know that our area, that has to do with this guy. And because we know this is the area of a sphere, and it's the surface area of a sphere, we can rewrite this as 4 pi r squared. It's very important to note that this is a little r, right? Because this is a variable r because it goes with this guy. All right, so it just has to be greater than or equal to the radius of the sphere, which is a constant, okay? So that gives us Q over epsilon naught. And if we just do some neat algebra and move stuff around, we can solve for E, which ends up being 1 over 4 pi epsilon naught Q over R squared. Well, fun fact, 1 over 4 pi epsilon naught is actually just K. So we can rewrite this as E for our sphere. And actually we don't need to write sphere, but just for R greater than or equal to R, right? So outside, that's going to be KQ over R squared, just like we thought it would be. So that means this matches with this, and we're all good. So the other thing that's important to note is this is only true for R greater than or equal to R because it says this was all calculated for the electric field outside a solid sphere, not inside. So now we have an expression for electric field outside the sphere. And if we want to write it as a vector, we just have to add the R hat back in. Okay, so now we're doing pretty much the same problem, but now we're doing inside the sphere. So this is sort of uncharted territory. We're not 100% sure what the answer is going to look like when we get to the end here. But we could probably guess, since we're only dealing with the charge enclosed, as our little r, as we go from 0 to the boundary of this sphere, we're probably going to assume that our answers should get bigger. So it should have like a linear or some sort of linear or bigger relationship. So as you enclose more charge, you get more electric field and so on and so forth. So we'll start with the same sphere that we had from the last problem, but let's make it a little bit bigger so we can see inside it easier. And once again, the electric field is going to go out radially in all directions. Just sort of envision that also going on inside the sphere. I'm not going to draw it this time, but that's the general idea. And once again, this is radius r. So we have to start with Gauss's law again. So Gauss's law looks like this. And we're going to start with that, which means we have to have some sort of Gaussian surface. So our Gaussian surface in this case is going to have to be inside the sphere. Once again, let me draw this sphere. So here's our Gaussian sphere that's inside our other sphere. So we'll make sure it lines up nicely. You can see this should be inside the sphere, so I'm just gonna try to indicate that here. And so here's our Gaussian sphere, and it should have a radius. We're gonna call this radius little r. I don't know if you can see that. Let me draw that with a little r. Okay, and this is our Gaussian sphere. And all of this is inside the bigger sphere. So it's enclosing some of the bigger sphere. And in this case, we need r to be less than or equal to big R instead of greater than or equal to big R. And once again, big R, right, little r is for the Gaussian surface, and big R is a constant, okay? So that's what we have going on with our values. So because we still have essentially an electric field that points out radially in all directions, including inside the sphere, that means at each point you have an electric field, and you also have your dA, right? So that you can see anywhere it crosses the boundary, that's going to be the case. And this little tiny sphere can get all the way down to 0 and all the way up to big R, which is a constant, right? That's the value. Big R is the radius of the actual charge sphere. So basically the red object is a real physical thing, and the yellow object is an imaginary thing that we use in order to get the math right, okay? So we've chosen this sphere of radius r that's inside of our big sphere for our Gaussian surface. And now, because of the way we chose it, the electric field is constant at all points and perpendicular to the surface at all points of this Gaussian sphere. So just like before, the beginning of this problem starts kind of the same way. You can see that the electric field that we're trying to find is going to be this dark red, and you can see that the Gaussian sphere is represented by this. So we know that the dot product goes away because of the parallelness of these two vectors. We know the electric field is constant, so we can pull it out, and that gives us dA. This is still going to be equal to Q enclosed over epsilon naught. We're going to deal with that in a minute. Once again, this becomes, 4 pi little r squared, because remember, this is the Gaussian and this is the electric field, okay? But now we get to this Q enclosed over epsilon naught, and Q enclosed now is a little bit more complicated than it was before. So let's talk about Q enclosed. Q enclosed in this case is going to be all of the charge from the red sphere that's now inside the yellow sphere, okay? And that is something that's a little bit different than what we were dealing with before. So we know that Q enclosed, we know this Q enclosed is going to be less than our total Q, right? Where our total Q is just the Q of this total charged sphere thing. And it has to be less than the total Q because you're taking some fraction of it. So we know we're going to end up with some fraction that's less than 1, okay? So the way we're going to deal with this is we're going to deal with charge density. And so dealing with the charge density, we know that this should be E times 4 pi r squared, but this is going to be rho times the volume enclosed over epsilon naught. And let me show you what I mean. So we have rho, which is the density of this whole thing, and that's going to be Q over the volume. So that's going to be this Q, this total Q, over the volume of this, the volume of this red object. So when we actually plug that in, that's Q over the volume of a sphere of radius r, right? So that's going to give us 4/3 pi capital R cubed, because remember this is the volume of the total sphere and the charge of the total sphere, okay? So that's our rho for this whole thing, all right? The enclosed volume is different, right? So this charge is part of the enclosed volume, and the enclosed volume should be equal to, it should be the volume enclosed by this sphere, the Gaussian sphere. The enclosed volume is the volume enclosed by the Gaussian sphere. So that's going to be 4/3 pi little r cubed, right? Because that's going to be the volume enclosed. So volume enclosed is enclosed by the Gaussian sphere. The density is going to be from the physical parameters of the physical object. Because remember, the Gaussian sphere is an imaginary thing, and then this is a physical thing. Okay, so the charged sphere is a physical thing. So we can write these in. So this becomes Q over 4/3 pi capital R cubed, because that's the total sphere, the physical actual charged sphere. And then we multiply that by 4/3 pi little r cubed, because that's the enclosed sphere. So here we have our, here we have our density from our actual object, and then this is this total volume that's enclosed by the imaginary object. So when we figure this out, we end up canceling some things, and let me just, let's pick something different, maybe a blue. So the 4/3 cancels, the pi cancels, and you end up with a fraction, which is what we were expecting. So we get Q r cubed over r cubed. But remember, this r has to do with the Gaussian, and this r has to do with your actual sphere. Remember, this still all equals to E 4 pi r squared. And because this r is also the r from the Gaussian surface, these are the same r. And we can, so just to clarify, remember this, we said that we would have a fraction of Q. We know little r is less than big R, so that's going to be less than 1. That's what we expected. But we also need to cancel some of these r's, so we end up with E. Oh, and I lost an epsilon naught here. It should be over here too. Anyway, we get 1 over 4 pi epsilon naught, which we know is K. Q over r cubed, these are all constants, times r. Okay, so this is going to be K, remember, because 1 over 4 pi epsilon naught is K, Q over r cubed, these are all constants, r. Okay, so that's our value, and remember we talked about what our electric field, we talked about, oh man, this is not working. So that's our electric field for R less than or equal to R. So inside the actual sphere. And if you want to make this, you know, a vector, it's still in the radial direction. But the important thing here is the relationship. We said that as we enclose more and more, so as we have circles that go out and out, we enclose more and more charge, and therefore we should have a bigger and bigger electric field. So it makes sense that this is linear. The other thing I want to point out, and let me move some of this stuff over so we have a little more space, is if you want to look at the electric field in all space, so from 0 to infinity, we have inside now, and we also have outside that we got from our last time. So in this case, electric field is linear with R, and in this case, electric field is inverse square with R, okay? And if you want to plot this, here you can have your electric field as a function of R. It looks like a linear relationship, and then, oops, and then an inverse squared relationship. So this value right here is capital R, right? This is R, here's 0. And then at this point, you have the electric field at the boundary condition, which is, this is going to be KQ over capital R squared, which is a constant, okay? So this is at the edge, right? So you start out inside the sphere. As you enclose more and more charge, you get more and more electric field, and then at the boundary of the electric field, it starts to drop off like a point charge. So this is linear, and this is inverse squared.